this is the first challenging problem in this chapter. So I need your attention. Okay. Many decisions result in a fixed or a lump sum cost being incurred. For example, the cost to lease, rent, or purchase a piece of equipment or a vehicle that is required if a particular action is taken. So in this situation, that cost to lease, rent, or purchase only happen once, right? It's like in economic analysis, it's kind of like the fixed cost versus say like the unit production cost will be like the variable cost. That depends on the unit of product you produce. Okay, and for example, the setup cost to prepare a machine or produce a different type of product. So this setup cost only happens once. Okay, if you use the machine, it will happen, but it only happens once. It's different from, say, the cost that happens that's related to how many products you produce. Okay, same as cost to construct a new production line. Okay, or cost of hiring additional personnel that will be accrued. So all those costs will happen only once if you are going to take this action, if you are going to construct this production line, or if you are going to hire. And there will be some additional, say, variable cost that will happen. And the total cost will depend on how many individual units you're going to have. So for this problem, I'll ask you guys to read the problem statement very quickly, and then we'll talk about them together. Okay, since I finished reading once, I believe you guys are finished. Okay, so at the first sight, this problem is not very different from, say, the Blue Ridge Hub problem. Okay, so 3 different types of products are produced, and the hours required on these 3 different process, okay, were also given. Total hours available are given. Without, and the cost accounting estimate that each product, 1 will make $48 of profit, product 2 will make 55 and 50. So if we just read through here, it's a very, very simple problem. Okay, you maximize the total profit, right? And at the same time, there are some constraint, which is the total hours available, total hours used to produce those 3 products should not exceed the total hour available. Okay. But after that, some additional conditions are added. Okay. So manufacturing a unit of product 1 requires a setup. Okay. Or to say, not just a unit, to say if you are going to produce product 1, any unit, okay, you need to set up this machine, and it costs $1,000. Okay, this $1,000 just happen once. If you're going to produce product 1, then it will happen once. If you're not going to produce product 1, then this $1,000 won't happen. Okay, same as for products 2 and 3. If you decide you're going to produce product 2, regardless of the number you're going to produce it, $800 will need to happen because that's the setup. Same as product 3, $900. Okay, so this adds some complexity to this problem. That okay, besides those unit profit making, it's no longer a simple problem that okay, we decide what's the total profit from here, and we decide how many products 1, 2, 3 to make. Here we need to consider those setup costs. Okay. And if we produce product 1, we need to subtract this setup cost. If we produce product 2, we need to subtract this this cost. If we produce product 3, we're going to subtract this cost. But the problem is that we don't know whether we're going to produce them before we know what's the optimal solution, before we know what's the optimal objective. Okay, the only way we can do is that somehow we need to include these values in our objective and turn them on if the related product is produced. and turn them off if the related product is decided not to be produced. Okay, and we know how to do that. We know how to turn those products on or off, include or not include, in the objective function. Because in the previous problem, we talked about how to turn the MPV on or off for a project that's to be selected or not to be selected. Okay, so one thing I want to emphasize in chapter 6, all the problems I selected, they go in the theory, and it's kind of like the knowledge you learn from one problem, you will need to remember that and try to relate to the next problem. Okay, otherwise it's really hard for you to formulate problem from scratch. If you remember what you learned from the previous problems, even some of the constraints, say, okay, for this logical statement, what's the constraint? If you remember that, it makes it really quickly for you to develop constraint for the more complex problem. Okay, like here, we talk about how to include or not include certain values in the objective function. Here, that's what we're trying to do. Okay, and for this problem, the basic part, or maybe let's talk about first. So what's the decision? What's the decision for this problem? How many of them to produce still, right? How many 1, 2, 3 product to produce? And if we produce, say, 0 or product 1, that means we're not going to produce product 1, which means this 1,000 setup cost will not happen. So the decision is still how many to produce, and this how many can be from 0 to a number that satisfies the constraints. Okay, so this table summarizes those key information here, and I'll use this table to write. Okay, so the decision variables, still we need to have our xi's. Okay, represent 1, 2, 3. Number of product I to produce. Okay, I goes from 1, 2, 3. Okay, so that's one of the decision variable. I just put like this. And our objective function, we said we're going to maximize the total profit. And we know that from the very basic problem here. These are the total profit we can get from producing the 3 products. Okay, there is a possibility that maybe one of the x will be 0, meaning we're not going to produce that type of product. If that's 0, then the profit won't be counted. Okay, and we said that we need to subtract those setup costs here. Okay, and we can just do this. We can just do this, because we don't know whether they will all happen, or one of them will happen, or 2 of them will happen. We can only include the decision variable to turn them on or off. So how do we do that? What did we do in the previous problem? A binary variable, right? And here, can we use x, 1, 2, 3? No, because these are not binary, right? They should go from 0 to a certain value. Okay, so we need to differentiate them. So let's just use y, okay? y1, y2, and y3. Okay, so with this, we include those setup costs, but we have introduced a mechanism to include or not include. Okay, so here, I'm going to introduce this y here equals to b. So the 2 different ways of defining them. Okay, 1 or 0. Product I. Oh, actually, I can do a simple way. That product I will be produced. Okay, otherwise, I'll just write down. Will be produced. Otherwise. Or a different way would be, I'll write it here. yi equals to be 1 or 0 if xi is greater than 0. If xi equals to be 0. So this is just a different way of defining your decision variables. Okay, either one works. Okay, so now we have this y binary variable. Constraint. First group of constraints really easy. Will be just the resource constraint, right? So 2x1 plus 3x2 plus 6x3 less than equal to 600. So basically those constraints here. So I will write them. So there will be 3 constraints here. Okay. And we need to have integer constraints, binary constraints. So xi are integers, yi are binaries. Okay, for all I goes from 1 to 3. Then, is that all? What do you guys think? If we have those constraints, what will be the final value for the y's if we just solve this way? There will be 0, right? Because we don't have any constraints on the y's. And when the problem is solved, we want to maximize this objective function. And, well, y can be 0 or 1, right? It's better to be 0 because we want to maximize this value. We don't have anything that's forcing those y value to be 1 in the constraint part. Okay, so that means we have a missing constraint. And that missing constraint is that we forgot to link this y with x. Okay, so we need to link our y, with x. That's what we wrote there. So y1 equals to be 1 or 0 if x1 is greater than 0. Okay, y1 will be 0 if x1 equals to be 0. So we'll just use y1 and x1 to illustrate this first. Let's see, how do we come up with a constraint that help us achieve this relationship? And this is a little more complex than the one that we just talked about. Say if project 4 cannot be chosen if 5 is also chosen. It's similar, but in that case, both are binary variables, right? In this case, y is a binary, but x is a non-binary, which means it can go to 1, 2, 3, 4, 5, 6 all the way. Okay. But let's think about, say, if x1 is binary, what happens? Can you relate to the logical statement that we talked about earlier? It's kind of saying, okay, if if they are both binary. Think about that. That's the project one. If 4 is chosen, 4 cannot be chosen unless 5 has to be chosen. Do you see similarity in this one? Say if x1 is chosen, we'll just say if x1 is produced, then y have to be 1. If it's not, if it's a 0, if it's not chosen, it has to be 0. If they are binary, what about if it's
well, that's the same thing as what I said.
okay, okay,
It's just defined differently.
okay. Then now it's not. Okay.
You could say y1 minus x1 is equal to 0.
Y1 minus x1 is equal to 0? Oh, it's the same. Okay. Okay. So maybe I'll give you 2 minutes to think about. You may need to introduce some value here, but remember this x1 is not a binary, so it can go to a bigger value. So maybe let's find out this first.
Are you asking if x was binary, what would be the constraints?
No. We'll drop that one. Okay. So let's find out what's the maximum value x1 can go. Can we find out what's the maximum value x1 can go? From here you can find out, right? Did you guys see how to find out that? What's the maximum value x1 can go? Divided by 2, right? Divided by 6 or divided by 5. What's the maximum value? So we're doing this assuming that we just produce product 1, no product 2 or 3. So this will be 50, right? This will be 80. So the maximum value that x1 can go is 50. Okay. 50. Okay, here. x1 can go from 0 all the way to 50. So it's not binary variable. And to achieve this relationship,
can you do an if statement?
no, that's why we said we need to use binary. We cannot do if statement. What we're trying to do is to change this if statement into a constraint using the binary variable. Okay. Think about it. Okay, so when y equals to be 1, x have to be greater than 0. So if x1 is a binary, we're just looking at the first one. Okay, if this is 1, yeah, x1 need to be greater than 0. So which means when y is equal to 1, x1 has to be forced to be greater than 0. If you think okay, if x1 is a binary variable, how do you achieve this condition? Just look at this one. If x1 is a binary, how do you achieve this condition? If this x1 is a binary, that means this one has to be 1. In the previous case, we used to say, okay, y less than equal to x1, right? If we use this condition, we are saying, okay, if y equals to 1, then we have to force this x1 to be not 0. It have to be greater than 0. So we use less than equal to here. And in this case, it works for y. Okay, but for, let me see. Yeah, then for if y1 is 0, x1 have to be 0. If it's this one, how do we know that make them equal does not work, right? Make them equal does not work. So maybe one thing let's go back to this objective function again. We'll look at this part first.
But the second statement, the first line covers the second one as well. You said y1.
Okay. Let me just, I forgot to mention this part. So we actually did. For this, with this objective function, if we don't have any constraints, what value will y take? Y will take 0, right? So what we need to do is just to force y to be 1 when it has to be 1. Okay. So which is this one? Because without any constraint, y will be 0 anyway. So this one will be the one that we focus on. And when yx, or the other way, when x is greater than 0, we want our y to be 1. The logic, maybe this way is more logical. Okay, when we decide to produce this product, when x1 is greater than 0, we want our y to be 1. We had this one here. Let's see if it works. So when x1 is greater than 0, if it's a binary variable, again, we'll say if it's a binary variable, that means x1 is 1. Okay. Then we want our y to be 1 too. So let me see. If it's a binary variable, our x will be 1. We'll just use this one again. If we use this condition again, let's see if we can achieve this relationship here. If x1 is greater than 0, which means it's not 0 value, then y is forced to be 1. Is that right?
That's what we want.
Yeah, that's what we want. That's with this condition here. If x1 is more than 0, oh, actually y1 can be 0 too.
You need to change this sign.
Inequality is vice versa. Y1 is greater or equal to.
Yeah, I know.
That's the point?
Yes. Yeah, so if x1 is more than 0, so if x1 is greater than 0, using this condition, this constraints, y can still be 1 or 0, right? If it's less than equal to. That's not what we want. We want it to be 1. Okay, so if we change the sign, I'll just change the x1 to the left-hand side. Okay. Let's change the sign. If x1 set it less than equal to y1, now if x1 is greater than 0, still if it's a binary variable, okay, if it's greater than 0, now it's 1, then we will be able to force y1 to be 1 using this sign here, because we set it less than equal to, right? And that's the purpose. We want our y to be 1. We tried this one, didn't work. When x is greater than 0, when it is 1, y can be 0 or 1, not what we wanted. But if we try this way, less than equal to, when x1 is greater than 0, which means if it's a binary, it will be 1. We will force y to be 1. Did this part make sense now? Just think if x1 is binary. If x1 is binary, this is 1. Using a less than equal to, 1 should be less than equal to a value that only be 1, right? Y cannot be 0, So that achieved what we want here. However, there is a problem. The problem is that our x1 is not binary. So it can go from 1 to 2 to 3 to 4 all the way to 50. What happens if it's a 50? 50 cannot be less than equal to a 1, right? So can we do something? Great. If we put 50 on this side, So still, this 50 will be fixed here. It won't change. But y can only be 1 or 0 value. So when this x1 start to increase to a value that's more than 0, say if it's a 1 or 2 or 3, all the way to 50, it will still force our y to be 1 because it cannot be 0. It can only be 1. And the condition is satisfied. All the value that x1 takes is less than this 50 because 50 is the value that we identify. That's the maximum value that x1 can be. Does it work now?
Or can you just multiply it by xi or x1?
No, because that will be a nonlinear. You are saying x1 times y1?
On the right side?
Right. Is that what you're suggesting? That will be nonlinear. Yeah. One mistake students often make in this chapter is they multiply the decision variables together. Because many of the problems you can solve that way. But they become nonlinear, and we don't want nonlinear. We avoid nonlinear as long as we can formulate ILP, because in nonlinear, it's not guaranteed you find the optimal solution. Oops. Okay, so with this, is this part clear? So the thinking process is that you try those different, so you think about what you want and find out, okay, logically, what should be the right sequence? For example, we started from here and didn't make much progress. Okay, we kind of think about this constraint. Okay, didn't make much progress, and we think, okay, actually, with the help of the objective function, y will be 0 anyway. So we only need to force it to be 1 when it has to be 1. So that means we need to force y value instead of forcing x value. And what forces the y value is the x. Okay, so we use the x to force the y value. So this is the right way to go, logically. Sometimes if you put the sequence opposite, it will be very hard to generate the constraint. Say, in this case, we want to force the y value, and it's the x value that forces it. Okay, then we try those different constraints. So, okay, maybe let's try this minus this, because we got this from the previous logical statement. Say like you select this one unless you select the other one. Logically, it's kind of like similar to this one. Say you produce this unless or you charge the fixed cost unless you produce the product. So it's kind of like logically similar. So you try those similar constraints, and you work for the x, y value. You say, okay, didn't work, cross it, and try a different way. So we tried, okay, let's flip the sign. And we try, okay, we try it, it worked for binary, but the value of y is really limiting this x to increase. Because x can go from 0 all the way to 50. We don't want to limit x1 value. So let's just multiply a value here. And that value is the maximum value this x1 can be. So you multiply that value here, and then you got already. I plugged it in. Oops. Is it charging now? Okay, so then we came up with this constraint here. Okay, so let's just summarize this part very quickly. Oh, actually, the next step, after you come up with, we're under time crunch here. Okay, after you came up with this constraint, try it again. Okay, so now we have x1 less than equal to 50 times y1. So with this, think about whether it fulfill your purpose. Okay, we want that if x1 is greater than 0. So if this is greater than 0, we want our y to be equal to 1. Okay, so worked. And if our x1 is 0, what happens with this constraint? If x1 is 0, with this constraint, what happens?
Y is forced to be 0.
x1 less than equal to. So a 0 value can be less than equal to.
It can be 0. Y can be 0 or
Y can be 0 or 1, right? Okay, so seems not working for this one. But we know that with the previous objective function, when y can choose between a value of 0 or 1, it will want to choose 0 only. So together with the objective function, together, okay, I'm not able to write it. You see, that's a reason you need to, once you came up with that constraint, you need to try that again to see it fulfill everything. So with that maximization objective function, together, you will force y to be 0. So that means, okay, both are satisfied. That's the constraint we need. Okay, so that's the process. So we came up with the basic variables, basic constraints. We find there is a missing constraint. And here, when we went through it, we find those big M first. Those big M represent the maximum value that your xi can be, okay, like the 50 there. And on the slide, I showed a specific way of finding the maximum value. So here will be the final constraint. For x2 and 3, you identify what's the maximum value you can get for 2 and 3. And you guys got it, right?
Got what?
This problem, fixed charge problem.
Yeah, I mean, it's intuitive once someone else has done it.
Oh, yes, exactly. And once you see a lot of problem examples, you recognize them. I guarantee this.
I have a question.
Yes.
Do you have to find the maximum value for x1, x2, and x3, or we
Right.
can just put some, like the big value? Like
Yeah, you can. Okay, so the question is that should we find out those exact value or just put a big value? I think it's better to find the exact value. And in this class, I will require you guys to find the exact value. Okay. Yes, you can put a really big value here, but one thing is that knowing those guarantee that the value is big enough. Secondly is that you guys all know how integer ILP solve slowly, right? When you tried it for chapter 3, because it look at all the different problem sets. And the bigger those values are, the much longer time it will take for the problem to be solved, because you kind of enlarge the searching area for the algorithm, and it will increase the searching time. Okay, sorry, I ran out of time, and let's do the presentation. So I will talk about those next time.